It was controversial, it was even banned in some countries, but it was undeniably ahead of its time. The technology it pushed to the limit made one thing clear. Being ahead of its time wasn't just an opinion, it was a fact. This video is the first in a 3-part series. Throughout the series, I'll explore 3 projects, their technical limitations, software architecture, and key technical concepts. I will draw parallels between 30-year-old game engines and modern systems. The goal is to show that, regardless of the industry we work in, there's a lot to learn from projects outside our own domain. This is Wolfenstein 3D. During the preparation for this video, I read the 2 books, Masters of Doom and Fabien Sanglard's game engine black book Wolfenstein. I highly recommend reading them both. So before we start, let me walk you through the roadmap of the video. First, we're gonna start with the technical difficulties that id Software had to overcome. Then, I'm gonna break down the software architecture of Wolfenstein. I will talk about the big picture, components, and how all of it works together. Then, I'm gonna unroll the main loop and talk about how the startup looks like. Last but not least, I'm gonna talk about specific concepts like recasting, heartbeats, fisheye correction, and the pseudo random number generator. During the video, I will make references to other projects, comment on best practices, and give you insights from other software industries. Now, why do we have to talk first about the technical limitations? These limitations have driven all the architecture decisions that have been made in this game. If you are a prompt engineer, I know this might blow your mind, but there are boundaries when it comes to software and hardware. So let's start with the hardware. During the 80s, gaming was dominated by consoles. They were just plug and play with no need to worry about hardware compatibility or software issues. And the majority of people is not even aware of these things when thinking about Wolfenstein, so stay with me now. Most game studios at the time focused on console development because it was just simply easier. Consoles provided a standardized platform designed for gaming. You didn't have to worry about hardware variations or any inconsistencies for that matter. I mean, a Super Nintendo is always a Super Nintendo. On the other hand, a computer was a completely different story. Everything was all over the place. Besides the fact that computers were designed for office jobs and not for shooting Hitler in the face with a machine gun. So id Software wanted to create something entirely new, a first-person 3D game. This level of real-time rendering demanded raw processing power, and if you compare the hardware of the time, PCs massively outperformed consoles. This gave the computer 2 major advantages: a fast CPU for handling real-time rendering and a 256 kilobyte VGA frame buffer. Okay, now let's talk about the architecture. Okay, so let me walk you through how I analyze anything. Now, without even looking at the code, we know that Wolfenstein is a game. And my goal is to sketch out how the system roughly looks like. First, we start with a black box. We know there are some inputs and there are some outputs, but we don't really know what's happening under the hood. Like when your bro fixes his own car and now there's a mysterious burning smell at every stoplight. Anyways, since this is a game, we have a user that is feeding this black box with input. A keyboard, mouse, controller, anything. And on the other side, the black box outputs something on a screen. In our case, we see the game running. Now, we know that Wolfenstein has no online multiplayer, so this will not be a client-server architecture like in the other games I reviewed. So we can assume that in the black box we have the engine, which is made out of components. These components can then communicate, in this case via shared memory. Now, the Wolfenstein engine is split into 3 parts: the 2D engine, the 3D engine, and the sound engine. We had something similar in the roller coaster video, a menu part and an engine part. The 2D engine is used for the menu, the 3D engine is where the renderer is located, and the sound engine is responsible for the sound system, which runs concurrently with either the 2D or the 3D engine. Now, as I said, these 3 parts communicate via shared memory. The interesting thing is that inside the sound engine, we have the heartbeat logic. The heartbeat logic is the time management of the game. It handles the time ticks and updates the time count variable, which you can imagine as some kind of wall clock. But why did they have to introduce this heartbeat logic? So the heartbeat logic was used because they couldn't use threads at the time or background processes. So you can imagine the heartbeat as some kind of manual scheduler. Before we continue, if you like the content, hit like and subscribe. Last time only 2.7% of my audience was subscribed to the channel. And now we are at 3.8%. We are so back, baby. And I wanna say a big thank you to my Patreons and YouTube members. VRL Petku, David Ziskovsky, my bro Joey Herschel, and Dr. Slowdeath. If you wanna help me get better equipment, you can become a Patreon. The link is in the description. Okay, now let's take a look at the software components in the source code. If we take a look at the source code, we will see that some files have this WL prefix and some this id prefix. These prefixes represent different layers. So the WL files represent a high-level layer and implement the game engine. The id files represent a lower layer, which includes so-called managers. The managers interact with the hardware. So you can imagine the WL layer as the application layer, and the id layer is something like a hardware abstraction layer, and then comes the hardware. Now, another interesting thing is that this id layer was reused from their previous game, Catacomb 3D. This is good practice. Create something that can be like a platform for your application layer, so you don't have to develop every time everything from scratch. Now let's go through the manager components. So the id layer has 7 managers in total. The memory manager. They decided to implement their own memory management, since using malloc would cause a lot of memory fragmentation. And since the memory was very limited, it was very important to use it efficiently as possible. Later on, John Carmack said it was probably justified to write an own memory manager for Wolfenstein, but he would urge people not to do it since it is a huge source of bugs. Then we have the page manager, which makes sure that assets like textures and sound stored on the hard drive are available in RAM for the CPU to use it. Video manager has 2 parts. A high-level component which is dedicated to 2D menu drawings and is a client of the lower layer, and the lower layer which is done in C and assembly. The C part abstracts away VGA register manipulation via assembly routines. Cache manager loads and decompresses assets stored on the file system and provides it to the RAM. Sound manager, which abstracts interaction with supported sound systems. User manager, it takes care of the text layout, so it doesn't really have much to do with the user. It handles the print routines and passes the information to the video manager, which then does the rendition. And input manager, which abstracts interactions with the input hardware like the mouse, keyboard, joystick, and so on. Now, if you put all these components in my black box and add the hardware peripherals, we get something like this. Okay, so at the top we have the WL engine. Then we have the id layer, the managers. Now, keep in mind that the cache and page manager communicate with the memory manager, and the memory manager then communicates with the RAM. Then comes the hardware layer. So we have the keyboard or mouse, the sound hardware, the RAM, and the VGA. The input manager communicates with the keyboard and mouse, the sound manager with the sound hardware, the memory manager with the RAM, and the video manager with the VGA. We can also mark the layers in different colors, so yellow is the top game engine layer, the green is the id layer with all the managers, and then the hardware layer is in pink. You have to keep in mind that id Software followed this design decision very strictly. So at no point could a component from the top layer directly communicate with the hardware. Okay, now we can copy this and say, okay, this is a closed system. And now we can add some user input. So if the user pushes something on the keyboard, it is handled by the hardware, then by the input manager, then it is sent to the engine. Then some other stuff happens in the engine, and then the video manager updates the frames in the frame buffer, and then we see an updated frame on the screen. This is of course a very high level top big picture overview. So a lot of things are happening in here. From the first keystroke to the updated frame, a lot of things happen. But okay, now that we have defined all the components, we can take a look at the main loop and try to unroll it. The source code is publicly available. I will leave a link in the description. Okay, so when you clone the repo, you can open this Wolf source directory and then look for wlmain.c, this file. And then if you scroll to the bottom of this file, you will get to the main function. Here we go. So the main loop looks like this. We have check for episodes, patch 386, init game, demo loop, and quit. So the first thing the software does is it checks if the assets are available. If anyone tried to compile some of the open source id games like Doom, Quake or Wolfenstein, you will remember that if you compiled it and tried to run it, it throws you the error that it can't find the game assets, the game data. Now after that it checks if the system has a 386 CPU, and if that is the case, it makes some patches that affect some integral division math operations. Now the init function starts up all the managers. It starts loading assets like fonts and textures, so if you go in there you will see that it starts the managers and then it loads the lookup tables for the walls, textures and so on. Then let's go back to the main loop, and the main loop continues with the demo loop. So the demo loop contains all the renderers, the 2D renderer and the 3D renderer. And if you go in there, we will see that at some point it starts the game loop. This is the 2D renderer. And if you go inside the game loop, we will see that it starts the play loop somewhere. This is the 3D renderer. Okay, so that's how the main loop in Wolfenstein 3D looks like. Now let's talk about the startup. So anyone who played Wolfenstein remembers this screen. This is called the sign on. Now, what is this? This is some kind of diagnostics dashboard. It shows you how much RAM is installed and if you will be able to run the game or not. And on the right side it shows you the identified devices. They created it so that the user knows why they can't run the game if that's the case. And in the case the system didn't have enough memory available, the user would read out of memory and the game just wouldn't start. Then after the sign on screen, the rating screen is loaded. Now keep in mind that at that time there was no official rating system for games. I mean, the game was published in 91 and the first rating commission was established in 94. Okay, so after this blue screen comes the menu phase, the 2D renderer. And after the 2D renderer, the 3D renderer takes over and the actual game finally starts. But how does the frame end up on the screen? So first we have the rendering in the system RAM. The game engine renders the entire frame into a buffer located in the RAM, because directly drawing to the VGA memory would cause flickering. Then it copies the frame from the RAM to the VGA VRAM, and in the last step the VGA hardware reads the frame stored in the VRAM and sends it to the CRT monitor for display. The CRT then scans and draws the frame line by line. And if you go an abstraction level deeper, the rendering sequence looks something like this. First, the frame buffer is cleared by drawing the floor and the ceiling, which both are in solid colors. Then starts the raycasting for each column, which is 320 in this case, so for each pixel. And the raycasting ends every time when it hits a wall. Then it renders every object with the size inversely proportional to the distance. Then it draws the sprites, the enemies, lamps and barrels, and then last but not least it draws the weapon. I will not go deep in the technical aspect how the renderer works, it is beyond the scope of this video. But if you want to read about it, I recommend reading the Wolfenstein Black Book, there is everything explained in detail. Okay, now I will take a look at some technical concepts that have been developed in Wolfenstein. So we will take a look at the following: raycasting, fisheye correction, heartbeat, and pseudo random number generator. So let's start with the raycasting. Now, raycasting is a rendering technique where you simulate a 3D environment by using a 2D map. I mean, Wolfenstein 3D operates technically speaking in a 2D world. But how does raycasting work? So you have the player and then, as the name says, you cast rays at different angles. And don't confuse raycasting with ray tracing, which is a lot more complex. All the modern games use ray tracing, but also ray tracing is not only used in game development, it is used in, for example, software for the optimization of optical systems. And I used to develop those when I worked at the Optical Physics Research Institute. Okay, so when performing raycasting, you cast rays to detect collision with objects. In this case, for example, walls or enemies. You have to keep in mind that in Wolfenstein 3D, everything is on the same level. You don't have stairs, for example, so that makes the rendering much easier. But now let's draw a sketch to make it easier to understand. So we have the player in the first person and we have the environment, the objects, walls, doors, and so on. To keep things simple, let's assume there are only walls. Now from the player perspective, we cast rays and check for collision with the walls. And then depending on distance, the engine renders the height of the object. So for far away objects, it calculates a smaller height, and for close objects, it calculates a bigger height. So far so good, but there's a problem. When you start calculating the height with this method, and you start drawing the frames, you will experience distortion, to be specific, fisheye distortion. When observing distant objects, this effect is not that problematic, but when you are very close to the objects, to the wall in this case, the effect is clearly visible. Therefore, they had to use another formula for calculating this distance. And this solved the problem and made the visual appearance of the game much more appealing. Let's take a look at two examples. On the left, you can see the uncorrected images, one taken from a distance and the other up close to the objects. On the right are the corrected frames. Now you're wondering, or maybe not, but Tariq, why would anyone care about this? Well, the same or very similar techniques are used in surveillance cameras, for example, or robotics. For example, you can take a fisheye lens, which has a very large field of view, and then you can correct the image distortion in software and get a much bigger picture, which at the same time doesn't suffer from the fisheye effect. So correcting this distortion is crucial for applications where accurate measurements, object recognition, or high quality images are needed. And in my opinion, this is very interesting, because if you think about it, this game was developed 30 years ago. And if you were someone who was developing some camera systems or something, you could have theoretically looked into the Wolfenstein source code and find a solution which would help you to create some advanced camera system, for example. Okay, now let's talk about heartbeats. Now, in Wolfenstein they introduced the concept of heartbeats. As mentioned in the beginning of the video, heartbeat was something like a central time management component. So they used the ticks to define time intervals between actions. We talked about ticks in the other videos if you remember. Now, this reminded me of a common trick in low-level embedded, especially on very old hardware with no real-time clock. The idea is to create a software-based clock by using the processor frequency and a simple loop to waste time in a predictable way. So something like this. We have a function called timer, then we have this count variable, and then we define the loop for wasting cycles. And keep in mind you have to adjust this 4000 to your CPU. In this example we assume a 16 MHz CPU with 4 cycles per loop iteration. And another thing is we need this volatile so the optimization doesn't remove the loop. Now this highly depends on your target hardware, so it's not a portable piece of software, but sometimes it does need to be portable. And this is of course not precise and not recommended in any way. You're not gonna build this into an airplane or something. And it also wastes a lot of CPU cycles and can be unpredictable. Okay, now let's talk about the pseudo random number generator. John Carmack decided to implement, instead of a random number generator, a lookup table with random numbers. And then every time the engine needed random, it would just pick a number from the table. Now, implementing a true random number generator or pseudo random number generator would not impact the gameplay in any visible aspect. I mean, the user would never be able to see any difference. So why would someone put effort into something that doesn't make any impact? And you should keep this in mind whenever you develop something. Is this making an impact or is it not making any impact? A lot of times I see people investing time into code sections that don't make any difference. But knowing in which section it makes sense investing time, that's called wisdom, and it comes with experience, with practice, okay? But now talking about this lookup table, this reminded me of something else. When I was working at this physics institute, we used to code physics engines for simulation software. So a major part of our software was using trigonometry functions like sine, cosine, tangents, and so on. And what we did is we created a lookup table in order to avoid calculating these values a billion times over and over again. And this small trick made the software run much faster. So lookup tables can be very handy when programming something that's calculating some values over and over again. Okay, so that's it for today. I hope you liked the video. The second part of this series is coming in the next weeks. And if you like the content, hit like and subscribe, and see you in the next one. Tariq 10x.